Welcome back to the Cisco NetAcad CCNA3 Enterprise Networking, Security and Automation lecture series. If you haven't seen my previous lecture series covering CCNA1 and CCNA2, I will leave links in the description for those playlists. I would recommend that you go through the previous CCNA lectures before you move forward with this course. Today, I will be covering module number 9, which is QoS concepts. The primary objective of this module is to explain how networking devices implement QoS or quality of service. We will cover network transmission quality, traffic characteristics, queuing algorithms, QoS models, and QoS implementation techniques. Network transmission quality. There's a video called The Purpose of QoS available to you through Cisco NetAcad. However, if you do not have access to this video, I have a copy posted to my YouTube channel. So I will leave a link in the description of this video as well as a card on the top right hand corner. So you can click on that and watch it. Please watch this video before we move forward with the next few slides. Let's look at prioritizing traffic. So when traffic volume is greater than what can be transported across the network, devices queue or hold the packets in memory until resources become available to transmit them. Queuing packets causes delay because new packets cannot be transmitted until previous packets have been processed. If the number of packets to be queued continues to increase, the memory within the device fills up and the packets are dropped. So if the buffer is filled up, then the packets start to get dropped. So one QoS technique is that can help with this problem is to classify the data into multiple queues as shown on the figure on the right hand side. So remember, none of the network systems anywhere in the world have been built with the transmission capabilities, bandwidth and transmission capabilities to transmit all the data all the time at continuous 100% rate, because it is impossible to do. So what happened is that when the volume of traffic is greater than what can be transported across a system, the devices in that system, such as the routers, gonna have queuing queuing implemented so that the packets will be queued in its memory when the network is busy. So then those queue packet will be sent out as soon as the resources become available. So in this example, we have the voice traffic, we have the financial transaction traffic and the web traffic all going through this router. And because the volume of traffic is greater than what can be transported across the system, so supported across the system, this router now going to use this QoS system, QoS techniques to try to manage that data that needed to be transmitted. So what the QoS or quality of service techniques are doing is that it is basically queuing all of this traffic according to different priorities. In this case, high priority, we're going to have the voice traffic. Medium priority, we're going to have the financial transaction traffic. And the low priority, we have the web traffic. And based on that priority levels, the QoS technique now going to transmit that data accordingly. So in this case, the high priority traffic, the voice traffic, which are time sensitive, will be transmitted first before any other traffic. So all communication types have some access to the media. One particular type of traffic cannot consume all the bandwidth in this way because it will be mixed among all of these three types based on the data and the congestion that the system sees. So device implement QoS only when it is experiencing some type of congestion, and when there is no congestion, let's say there is only voice traffic at a moment, so then the QoS implementation will stop. So it will only act on when there are multiple data streams coming into the device. So in most networks, whether it's a home network, home office network, or large corporation network, you will almost always have multiple streams of data, whether it's voice traffic mixed with financial transaction and web traffic. It could be gaming, like if you're at home, you're gaming and the games cannot get delayed because it will create jitter and etc. So those traffic along with your web traffic, like just somebody in your house accessing a website, those need to be differently prioritized. So the game traffic need to have the high priority, while your family member who's accessing the websites can have the low priority, for example. So what you need to understand is prioritizing traffic. The primary purpose of that is to manage the queuing done by the devices, so that all the traffic get a fair chance and a proper option for transmission. So remember that. So if the number of packets, however, on the queue continue to increase, the memory within the device filled up and the packets start to drop, that also will have an impact on the quality of service. Bandwidth, congestion, delay, and jitter. Network bandwidth is measured in the number of bits that can be transmitted in a single second, or bits per second, or BPS. Please make sure you understand that concept, because most ISPs will throw out words such as bandwidth and other related terms that may confuse you. So make sure that if somebody asks you what is network bandwidth is measured in the number of bits that can be transmitted in a single second, or bits per second. We also use the BPS for that, this term as well. So the network congestion causes a delay. An interface experiences network congestion when it is presented with more traffic than it can handle. The network congestion points an ideal candidates for QoS mechanism. So the network congestion happens because there is more traffic in the system than the device can handle, the interface can handle. So that's what causes the network congestion. The typical congestion points are aggregation, speed mismatch, and LAN to WAN. So those are typical points where you can implement QoS to improve your network. So aggregation happens in a situation where you have, for example, a switch with multiple ports in use on the LAN side. Well, let's say that you have that switch connected to a router with one single link. So what happened here is, even though on this side there are multiple connections to this switch with maybe, let's say, 1000 megabyte per second, this link is just one single link, 1000 megabyte per second going to the router. So it's going to create a bottleneck type of situation when the traffic is flowing from this side to this side. Hence, it's going to create network congestion right here. So this is a good place to implement a QoS. Speed mismatch situation happens where the traffic is flowing from a higher speed system to a lower speed system. So you have a network with higher speed to a network with lower speed. That, again, as you can see, when it goes across the switch, the data that can handle, the bandwidth it can handle on this side is much higher than the bandwidth it can handle that side. As a result, what's going to happen is you're going to create congestion here. So you can implement a QoS mechanism to make sure that you get best performance out of your network. The LAN to WAN situation is a very common situation that you see in homes, small businesses, as well as even some large offices as well, because in this situation, imagine you have a router, so like an edge router that is connected to the internet. Internet is the WAN, right? So your internet speeds most likely going to be slower unless you probably have like fiber to home, fiber to the site type of network. Most likely your internet speed going to be slower than your internal network. So if your internal LAN have 1000 megabyte per second and all of those devices trying to access the internet via this one link that is connecting to the outside world through your modem, that gonna create again a bottleneck type of situation when the traffic flow from the inside LAN network to outside WAN systems. So again, here is a really good place to implement QoS. This is a very common place to implement QoS, especially when you have things like voice over internet protocol, VoIP systems. Also, when you have gaming, like when you are doing gaming and your mom or dad want to access the internet, or your family member want to access the internet to visit a website, and someone else also want to access their financial transaction or something like that, you can implement QoS in here so that everybody have a good experience using the network. So the quality of service will be properly allocated, because games cannot handle delay, but the websites can. So you can use that to make sure that everybody get the fair share of their bandwidth usage. So when you go and buy a internet service from your internet service provider, you might get a router modem combination. And nowadays in Canada, at least, I've seen that most internet service providers will give you a router modem combination with QoS already set up in the system. So the modem router combination that you get from your ISP will already have the QoS implemented. However, it is customizable in most cases. So the end user most likely can customize it. And there are situations you will have the modem only, but you're going to implement your own router, and you should go ahead and implement those QoS systems and QoS techniques, because that will improve your network usage. So for most home users who just buy the internet from an ISP and ISP is providing that router modem combination, the QoS is most likely will be already set up for you. But as a network technician student or a network engineering student, you should always tinker with it to get the best possible outcome for your network. So in a corporate environment, definitely you're going to do it. For your home environment, you may not have to do it because it's already set up that way. But however, you can play with it until you get the best possible outcome. Delay or latency refers to the time it takes for a packet to travel from the source to the destination. Fixed delay is the amount of time a specific process takes, such as how long it takes to place a bit on the transmission media. Variable delay takes an unspecified amount of time, and it is affected by factors such as how much traffic is being processed. Jitter is the variation of delay of received packets. So these are key important concepts that you should understand for your exams and quizzes in this particular Cisco class. So the delay is the amount of time a specific process takes. And then the variable delay is a situation, just like it says variable, it is an unspecified amount of time that might take due to different factors of how the traffic is being processed. And the jitter is a variation of delay of received packets. So here is a table explaining certain types of delays and the descriptions associated with it. And you should know each one of these and how they are differ from each other, and you should be able to explain this during an exam. So the code delay is the fixed amount of time it takes to compress data at the source before transmitting to the first inter-networking device, usually a switch. So that is called a code delay. Packetization delay is the fixed time it takes to encapsulate a packet with all the necessary header information. Just like it says packetization, the packet, it's in that term. It is a time it takes to encapsulate that packet with all the necessary header information. Queuing delays is the variable amount of time a frame or packet waits to be transmitted on the link. So that's a queuing delay. That's where we can play some, we can apply some mechanisms to, right? The queuing delays. So with the QoS, we can play with that a lot. So the queuing delay is the variable amount of time a packet or packet waits to be transmitted on a link. A serialization delay is the fixed amount of time it takes to transmit a frame into the wire. So the time that it takes to transmit the frame all into the wire itself is called the serialization delay. Propagation delay is the variable amount of time it takes for the frame to travel between the source and the destination. That's called the propagation delay. It's the amount of time that a packet or a data, or in this case it's the frame, needs to be traveled from the source to destination. De-jitter delay is the fixed amount of time it takes to buffer a flow of packets and then send them out in evenly spaced intervals. So it basically try to prevent the jittering by de-jittering, but it's going to create a delay, and that most likely going to be a fixed amount of time that it will take for that buffer to work. So as you can watch this video on YouTube, YouTube is using those de-jitter delay, because you will see that the video get buffered if you have a slow internet speed, especially as you watch my lectures. So that is an example of a de-jitter delay. Packet loss. Without quality of service mechanism or QoS mechanisms, time-sensitive packets such as real-time video and voice are dropped with the same frequency as data that is not time-sensitive. So if you don't have QoS, the system doesn't know or doesn't implement any way of identify those packets. So as a result, it's just first come first serve, right? So basically, without QoS, all the packets, regardless of whether it's time sensitive or not, going to have the same priority and will be dropped at the same frequency no matter what. So when a router receives a real-time protocol, also known as RTP, digital audio stream for voice over IP, or VoIP, also known as VoIP, it compensates for the jitter that is encountered using a payout delay buffer. The payout delay buffer buffers these packets and then pays them out in a steady stream. So if you have, when the real-time protocol RTP implemented, the digital audio stream of voice over IP, for example VoIP, it compensates for that jitter that is encountered using the payout delay buffer. So basically, let's say you have an audio stream that's receiving with jitter, so it's coming in a different interval. So payout delay buffer going to make sure that it's going to be de-jittered and stream sent out to the outbound interface with the correct sequence. So that's what it's doing. So that's what the RTP going to do for VoIP. If the jitter is so large that it causes packets to be received out of the range of the play out buffer, the out of the range packets are discarded and dropouts are heard in the audio. So basically heard in the audio. So basically what's going to happen is that if you're listening to someone speaking over VoIP, and if the jitter is so large that it causes a packet to be received out of the range of which the payout delay can handle, as a result, what you're going to hear is the dropouts on your connection, which is pretty bad. For losses as small as one packet, the digital signal processor, also known as DSP, interpolates what it thinks the audio should be, and no problem is audible to the user. So it's if a loss is just a one packet, the DSP would be able to recover that. But when the jitter exceeds that the DSP can do to exceed what DSP can do to make up for that missing packets, the audio problems are clearly being presented. So if there is just one packet losing once in a while, the users may not experience any issues on the VoIP system. But if the jitter exceeds the DSP, what the DSP can handle, that would result in pretty much the audio problems for both end users, so the whoever on the both side of the call. So in a properly designed network, the packet loss should be near 0 or 0. So it's almost impossible to have a packet loss of 0. So it should be almost always near 0, but sometimes you can even achieve the 0 if properly design your network. Traffic characteristics. There's a video called Traffic Characteristics available on your Cisco NetAcad or through your academic institution. If you do not have access to this video, I will leave a copy of this video on my YouTube channel and a link in the description for it. I will also post a card on the top right hand corner, and I would recommend that you watch this video before you move forward with the next few slides. Network traffic trends. In the early 2000s, the predominant type of IP traffic were voice and data. The voice traffic has a predictable bandwidth need and known packet arrival times. So voice traffic has a predictable bandwidth need and we have a known packet arrival times. Data traffic is not real time and has unpredictable bandwidth need. Data traffic can temporarily burst as when a large file is being downloaded, and this bursting can consume the entire bandwidth of a link. So if you have a network where a bunch of people are accessing websites, it may be just regular data traffic with no burst in it, but then suddenly somebody start to download a large file from the internet, that could create a burst, a temporary burst on your network, consuming all your bandwidth. More recently, video traffic has become the increasingly important to business communications and operations. According to Cisco Visual Networking Index, also known as VNI, the video traffic represented 70% of all traffic in 2017. By 2022, video will represent 82% of all traffic. Mobile video traffic will reach 60.9 exabytes per month by 2022. The type of demands that the voice, video and data traffic place on the network are very different. And one key thing I also want to add is with the COVID-19 pandemic, where a lot of people working from home, the voice and video traffic become more and more important to network engineers, because now a lot of people are working from home. A lot of meetings and office related activities often happen through voice and video conferencing, which is causing a more usage of network by those activities. So I would say it is even greater than 82% at this time. So let's look at voice. Voice traffic is predictable and smooth and very sensitive to delays and drop packets. So the voice packets are predictable and smooth. However, they are very sensitive to delays and drops. Voice packets must receive a higher priority than other types of traffic, such as data traffic. Cisco products use the RTP port range 16,384 to 32,767 to prioritize the voice traffic. Voice traffic can tolerate a certain amount of latency, jitter, and loss without any noticeable effects. Latency should be no more than 150 milliseconds. So on voice traffic, the latency should be no more than 150 milliseconds. The jitter should be no more than 30 milliseconds and the packet loss no more than 1%. With voice traffic require at least 30 kilobyte per second of bandwidth usage. So these key pieces of information is very important for your exams and understanding the concepts behind voice traffic. So if somebody asks you what is the maximum latency a voice traffic can handle, you should be able to tell me it is 150 milliseconds. You should know the jitter should be more than 30 milliseconds and the loss should be no more than 1%. And you should also know the voice traffic require at least 30 kilobyte per second of bandwidth or it doesn't work. So these are key pieces of information you should remember for your exams and quizzes, as well as for your future network engineering careers. As far as the RTP port range goes, for your Cisco exams, you should know this port range. But for everything else, it's not something that you really need to know. So on the bottom of your screen, there's a summarization of what is really important with voice traffic that you should know. So the voice traffic characteristics are smooth, benign, drop sensitive, delay sensitive, and they are UPD priority. Yeah, right? So you should know all of that. And you should know that the latency of the voice traffic should be less than 150 milliseconds. Jitter must be 30 milliseconds or less, and the loss has to be at least lower than 1% with the bandwidth at least 30 kilobyte per second. But we recommend bandwidth between 30 kilobyte per second to 128 kilobyte per second. And you should know this for your exams and quizzes, and you should know this for your future network engineering careers. So let's look at the video. Video traffic tends to be unpredictable, inconsistent, and bursty. Compared to voice, video is less resilient to loss and has a higher volume of data per packet. So compared to voice traffic, video is less resilient to loss. However, it also means that it requires a higher volume of data per packet. The number and size of video packets varies every 33 milliseconds based on the content of the video. So UDP ports such as 554 are used for the real-time streaming protocol, also known as RSTP, and should be given priority over other less delay sensitive network traffic. So if you have data traffic, those should have less priority over the UDP port such as 554, which is used for RSTP. Latency should be no more than 400 milliseconds. Jitter should be no more than 50 milliseconds, and the video packet loss should be no more than 1%. The video traffic requires at least 384 kilobytes per second of bandwidth, otherwise it would not work properly. So again, for your exams and quizzes as well as for your future network engineering careers, you should know that the video traffic use the UDP ports, but you don't need to know the exact port number, but you need to know video traffic is typically using UDP as opposed to TCP. So video is usually UDP, almost never TCP. So the UDP ports are used in the video streaming protocols such as RSTPs, and the jitter should be no more than 50 milliseconds. The latency should be no more than 400 milliseconds. And the data packet loss should be less than 1%, and the video traffic must need at least 384 kilobytes per second of bandwidth. So on the bottom of this screen, these are the items that you must remember for your exams and quizzes, and these are key things that you should get out of this slide. So the video traffic is bursty as opposed to voice traffic, not very predictable. So the voice traffic are predictable, but the video traffic is bursty. So it is very greedy, drop sensitive, delay sensitive, and video traffic almost always use UDP. So UDP priority should be there, and you should have a latency less than 400 milliseconds. You could have between 200 to 400, but just remember 400 milliseconds. Jitter should be no more than 50 milliseconds. So it should be no more than 50 milliseconds. The loss should be no more than 1%, and the bandwidth should be between 384 kilobytes per second to 20 megabytes per second. So that is the key pieces of information that you should remember for your video traffic. So let's look at data. Data or data, either would be fine. So data applications have no tolerance for the data loss, such as email and web pages that use the TCP to ensure that if the packets are lost in transit, and they will be resent. So data applications that have no tolerance for data loss, such as email, web pages, they use the TCP to ensure that if the packets are lost in transit, and then they will be resent. Remember, as opposed to UDP, TCP is reliable. So you can use TCP for emails and web pages to ensure that the reliability is maintained. But this also means that unlike UDP, it's going to be a little bit of slower transmission than the, TCP is a little bit of lower transmission than the UDP. That's why we use UDP for video traffic and voice traffic, and TCP for data traffic, right? So data applications have no tolerance for data loss. However, because we are using TCP, which allow us to make sure that the transmission is good, because it is a reliable transmission. Data traffic can be smooth or bursty, as I mentioned before. Network control traffic is usually smooth and predictable. So if you have some type of a network control in that traffic, you can make it smoother and predictable. Some TCP applications can consume a large portion of network capacity. FTP will consume as much bandwidth as it can get when you download a large file, such as a movie or a game or a large CAD file by your engineering department, for example, accessing your engineering server with large CAD designs. That could consume a lot of data, because the FTP download would actually use up all of those bandwidth. So what you need to remember for data is that data can be either smooth or bursty. So depending on whether you're accessing a website or downloading a large file, it could be smooth or bursty. It can be benign or it could be greedy. So it could be either or as a result of that. However, data is drop sensitive. So that's why we are using TCP protocol, and delay sensitive. So the TCP makes sure the drop sensitive, delay sensitive issues will be taken care of by retransmitting those packets that has not been sent. However, one of the key difference between data compared to the voice and video traffic, especially voice traffic, is that it is not time sensitive. So if there is a delay in the packets when you are trying to reach a website, the website may load a little bit slower, but it's not going to make a big difference for you. Unlike the other ones we have, where you have a situation if a voice packet get dropped, it will have a huge impact on your quality of service. So data traffic will have a minimal impact on certain delays, because the TCP going to retransmit and make sure that you would be able to view that web page anyway. Data traffic is relatively insensitive to drops and delays, as I mentioned before, compared to the voice and video. The quality of experience, or QoE, is important to consider with data traffic. So instead of QoS type of thing, we're going to think about quality of experience, or QoE. This is probably a new term that you probably heard here right now, because QoS is commonly being used everywhere, but I hardly hear the term quality of experience. But when it's come to point data, what we are looking mostly is the QoE. So what is QoE? The QoE is in QoE, what we look at is, does the data come from an interactive application? Is the data mission critical? So those are the two questions that you would ask when you are thinking about quality of experience. So the experience for the end user, right? If the data is coming from interactive applications where the user is interacting with that application using that data traffic, or is it just also is the data is a mission critical, such as let's say a medical application that is really important, to have that priority set up there, right? So on the bottom of the screen, it's showing those factors. So the interactive or not interactive in here. So the mission critical and not mission critical. So this is like a table that describe how you can combine those concepts, but all these two questions together to decide what to do, right? So if it is interactive and mission critical, you need to prioritize for the lowest delay of all data traffic and strive for 1 to 2 seconds response time. However, it is interactive but not really mission critical, then the applications could benefit from a lower delay. If it is not interactive but mission critical, the delay can vary greatly as long as the necessary medium bandwidth is supplied. If it is not interactive and also not mission critical, gets any leftover bandwidth after all voice, video and other application needs are met. So this is going to be the lowest priority. So if the data that people accessing, such as just accessing a website like Sanuja.com, it's not interactive and it is not really mission critical at all, in that case, that access to that website, Sanuja.com, gonna get the leftover bandwidth after all voice, video and other data applications needs have been met. So that's how you look at the interactive, non-data interactive, mission critical and not mission critical in a QoS sense. Queuing algorithms. So there is a video called QoS Algorithms, which is available to you through your Cisco NetAcad. But however, if you do not have access to this video, I will post a copy of that onto my YouTube channel, and I will leave a link in the description for it, as well as a card on the top right hand corner. And I would recommend that you watch these videos before we move forward with the next few slides. So let's look at the QoS queuing overview. So the quality of service policy implemented by the network administrator becomes active when the congestion occurs on the link. So remember that the quality of service policy only become active when the congestion is there on the system. So the queuing is a congestion management tool that can buffer, prioritize, and if required, reorder packets before being transmitted to the destination. A number of queuing algorithms are available that are being used in the QoS. They include the first in, first out, or FIFO, which is basically having no QoS at all. Whichever the packet gets into, they are first gonna go out. Weighted fair queuing, WFQ. Class-based weighted fair queuing, which is CBWFQ. And low latency queuing, also known as LLQ. And I will cover these items in the next few slides. So first in, first out. Just like it says in plain English, first in, first out, basically a queuing buffers and forwards packet in the order of arrival. Just like it says first in, first out. So whichever the packet comes in first will get buffered out and forward out from the system. So the first in, first out, or FIFO, has no concept of priority or classes of traffic and consequently makes no decision about packet priority. There is only one queue and all packets are treated equally. Packets are sent out in an interface in the order in which they arrive. So in this case, you can look at first in, first out of FIFO as a method of forwarding packets without basically any kind of quality of service or QoS implementation at all. So whatever the packet comes into the queue first, just get buffered out and forwarded out as soon as it arrives. So it doesn't matter whether it's a voice traffic, doesn't matter whether it's a data traffic, it doesn't matter whether it's some kind of a web traffic. Whichever the packet arrived at the interface, gonna get forwarded out first in the first in, first out basis. So that is what the first in, first out algorithm is. So the next one is the weighted fair queuing, also known as WFQ. So the weighted fair queuing is an automated scheduling method that provides fair bandwidth allocation to all network traffic. WFQ applies priority or weights, we call them, to identify traffic, classified it into conversations or flows, and then determines how much bandwidth each flow is allowed relative to the other flows. So how that works is basically now the packets coming in is being weighted and being identified, and those classifications now will be put into conversations or flows, and then that would be used to determine how much bandwidth of each flow will be allowed to use relative to each other. Therefore, the WFQ classified traffic into different flows based on the source and the destination IP addresses, MAC addresses, port numbers, protocol, and type of service, also known as TOS value. WFQ is not supported with tunneling and encryption because these features modify the packet content information required by the WFQ for classification. So keep that in mind. So in weighted fair queuing, it is not being used or cannot be used with the tunneling and encryption, because the data that required for WFQ in those packets will not be there as a result of using tunneling and encryption. So on the right hand side, we have a image describing how weighted fair queuing works in an easy way to remember. So basically you have a data stream that coming in with priority classification high, normal, medium, and low. So that's what it is coming in, and then the high get classified into high stream, the medium getting into that, and normal, etc., etc. Then those queues then get out of the exit interface, we call it egress interface. Remember from our previous lectures. And the input interface is called ingress interface, and the exit interface called egress interface. So those then get sent out based on that weight that we see in each of those streams. So that's how the weighted fair queuing work. So one of the key things you should remember is that WFQ is not supported in tunneling and encryption. Class-based weighted fair queuing, also known as CBWFQ. So in the class-based weighted fair queuing, what it's doing is it extends the standard WFQ functionality to provide support for user-defined traffic classes. So what CBWFQ is differ from WFQ is that it extends the support of the WFQ to support the user-defined traffic classes. Traffic classes are defined based on match criteria, including protocols, access control lists, also known as ACLs, and input interfaces. So if you recall ACLs from my previous lecture on ACL, remember what the ACL are doing to traffic. So that these traffic classes are defined based on match criteria, based on not only protocols but also ACLs and input interfaces. Packets satisfying the match criteria for a class constitute the traffic for that class, and in a FIFO queue is reserved for each class, and traffic belong to a class is directed to the queue for that class. So FIFO is used after the classification has been done in this situation. So first we get the packet satisfying the match criteria for a class, and then that class is used to create the queues, then use FIFO first in first out on that class, and then the traffic will be forwarded accordingly. A class can be assigned characteristics such as bandwidth, weight, maximum packet limit. The bandwidth assigned to a class is guaranteed bandwidth delivered during congestion. So remember that the bandwidth assigned to a particular class, for example, if you have voice over internet protocol, so if you have VoIP data that can't have any delays, that could have the highest bandwidth assigned to it. As a result of that highest bandwidth class assigned to that VoIP, it is guaranteed bandwidth delivery for that VoIP traffic, no matter what its congestion is. The packets belonging to a class are subject to the bandwidth and queue limits, which is the maximum number of packets allowed to accumulate in the queue that characterize that class. So remember that. So these are some basic information about weighted fair queuing, which we're going to continue on our next slide as well. So after a queue has reached its configured queue limit in this CBWFQ situation, adding more packets to the class causes tail drop or packet drop to take effect, depending on how class policy is configured. So remember that. The tail drop discards any packet that arrives at the tail end of a queue that has completely used up its packet holding resources. So if you have these classes, let's say class 1, class 2, class 3, but the class 3 is now full because it only can maximum hold those 2, and as a result, when the next packet comes in, it's going to drop that packet because that class line is full, even though the other 2 classes may have enough room to put something else in there. Because it is coded for class 3 is going into the class 3 queue, right? So this is the default queuing response to congestion. The tail drop is the default queuing response to a congestion. The tail drop treats all traffic equally and does not differentiate between classes of service. So remember that the tail drop treats all traffic equally and does not differentiate between classes of service. So traffic is grouped into user-defined classes, and then they're divided into those different classes here, and weighted fair queuing methodology is being used in the CBWFQ as well. And also remember the first in first out is used in those each individual classes, and then it get exited out of the egress interface. So one of the key things you should remember is this: the default queuing response to congestion default queuing response to a congestion is the tail drop, and then the tail drop treat all traffic equally and does not differentiate between classes of service. So that's an important concept. Next, we're going to look at low latency queuing, or LLQ. So in low latency queuing, what happens is that brings strict priority queuing, also known as PQ, to that CBFW. So it's built on top of what we already do with the CBWFQ. So we basically take this one and then we build on top of that to create the low latency queuing, or LLQ. So the strict PQ allows delay sensitive packets such as voice to be sent before packets in other queues. LLQ allows delay sensitive packets such as voice to be sent first before packets in the other queues, giving delay sensitive packets preferential treatment over the other traffic. Cisco recommends that only voice traffic be directed to this type of priority queues. So what LLQ allow you to do is that on top of the CBWF queue, you're going to create a separate queuing using the low latency queuing, and you can direct specific traffic onto that. And by doing so, what's going to happen is traffic that belong to things like voice traffic, which is delay sensitive traffic, can be then channeled through that queue. But however, because of to get the maximum out of the LLQ, it is usually recommends that only voice traffic to be directed onto this priority queue, so that if the priority queue doesn't get congestion as a result of having too much traffic coming into that priority class. So remember that LLQ is building on top of the previous one, WFQ, as well as the CBWFQ. So it's in building. So it started with WFQ and it's going to build on top of that the CBWFQ, and on top of that we can use the CBWFQ along with the LLQ to give priority and the quality of service for the voice traffic. So again, these are the basic concepts of queuing methodologies that you should understand. And next we will talk about QoS models. QoS models. There's a video called QoS Models available to you through your Cisco NetAcad. But if you do not have access to that, I have a copy of that video posted to my YouTube channel. I will leave a link in the description of this video so you can go and watch it, as well as a card on the top right hand corner. And I would recommend that you watch this video before you move forward with the next few slides. Selecting an appropriate QoS policy model. There are 3 models for implementing QoS. QoS is implemented in a network using either IntServe or DiffServe. IntServe provides the highest guarantee of QoS. It is very resource intensive and therefore not easily scalable, however. DiffServe is less resource intensive, however, it is more scalable. IntServe and DiffServe are sometimes co-deployed in network QoS implementation. So those are the key things that you should understand. So on the bottom of the screen, it summarizes some of those things that describe up here. So we have the model called the best effort model, which is basically not an implementation of as QoS, is not that it is explicitly configured. So use when QoS is not required. So the best effort model basically says pretty much first in, first out. So whichever the packet gets into the ingress interface first, that's going to be the first one out on the egress interface. So that is called the best effort model. So it is not an implementation as QoS is not explicitly configured. So that's a very important. This might show up on your exams. So if they could ask, is the best effort model is a QoS model? Well, not really, because it doesn't have QoS implemented at all. The integrated services, also known as IntServe, so this is the next model that provides very high QoS to IP packets with guaranteed delivery, defines a signaling process for applications to signal to network that they require special QoS for a period, and that bandwidth should be reserved. So in this method, the integrated services allow you to do a way that it can define a signaling process for applications to signal to the network that they require special QoS for period, and that bandwidth then should be reserved as a result of it. ENSA can severely limit the scalability of a network because of the way that it is implemented. Differentiated services, also known as DiffServ, however, provide high scalability and flexibility in implementing quality of service. Network devices recognize traffic classes and provide different levels of QoS to different traffic classes in this situation. So now let's look at the best effort model. The basic design of the internet is pretty much on best effort packet delivery and provides no guarantees. So if you just look at how the internet works, or how typical network with no QoS explicitly implemented, that would be actually doing the best effort model. The best effort model treats all network packets in the same way. So an emergency voice message is treated the same way that a digital photograph attached to an email is treated. So there is no differentiation in the packet stream. Benefits and drawbacks of the best effort model are described on the bottom of your screen with this table. So the benefits of the best effort model is the model is the most scalable. So it's very easy to scale, and scalability is only limited by the available bandwidth, in which case all traffic is equally affected. So if the bandwidth is a limiting factor, in most cases it is, that all traffic will be equally impacted, not one over the other. No special QoS mechanisms are required. So technically the best effort model, as I mentioned before, is not really QoS, and it is the easiest and the quickest model to deploy because it's just first in, first out. Drawbacks, however, is that there are no guarantees of delivery of packets. Packets will arrive whenever they can and in order possible, if they arrive at all. So whenever the packets arrive, and in the whatever the order it's arrived, and that's how those packets gonna get forwarded, and no modification of how packets are being forwarded are done. No packets have preferential treatment. So if there is a voice packet, if there is a data packet, it doesn't know how to separate the data packet from the voice packet. It's just gonna send those data forwarded as it is. Critical data is treated the same way as email is treated, as I mentioned above, because it's just best effort. Integrated services, or INTServ. So the integrated services delivers the end-to-end QoS that real-time applications require. So if there are applications in your network that require real-time need, that this is what it is used for mostly. So what integrated services do, it explicitly manages network resources to provide QoS to individual flows or streams, and sometimes called micro flows. So it is explicitly managing those streams. It uses resource reservation and admission control mechanisms as building blocks to establish and maintain QoS. It also uses a connection-oriented approach. Each individual communication must explicitly specify its traffic, decipher, and requested resources to the network. So each individual communication will be explicitly managed and defined in the stream. The edge router performs admission control to ensure that the available resources are sufficient in the network. So on the right hand side, here is an example of it showing it's using dynamic resource reservation on these routers, and the QoS aware nodes will be used in this situation to do the integrated services in this system. So in the integrated services model, the application requests a specific kind of service from the network before sending data. The application informs the network of its traffic profile and requests a particular kind of service that can encompass its bandwidth and delay requirements. So basically, let's say it's a VoIP traffic. It's a VoIP application going to inform the network, hey, this is my traffic profile and I need this kind of quality of service and bandwidth, and I have this kind of a delay requirement in order for me to be successful. So the VoIP traffic in this situation going to inform the integrated services, this is what we need to do. So INTSERV uses the Resource Reservation Protocol, also known as RSVP, to signal QoS needs of an application's traffic along devices in the end-to-end path through the network. So based on that information, the INTSERV uses the RSVP to signal the QoS need across the network from end to end. If network devices along the path can reserve the necessary bandwidth, the originating application can begin transmitting. If the requested reservation fails, however, along the path, the originating application does not send any data. So that's a key feature of the integrated services. So on the bottom of your screen, we have some benefits and drawbacks of integrated services listed. Benefits include the explicit end-to-end resource admission control, per request policy admission control, and signaling of dynamic protocol port number. The drawbacks includes the resource intensive due to the stateful architecture requirement for continuous signaling. So it requires a lot of resources to do that continuous signaling. And also flow-based approach, not scalable to large implementations such as the internet, because that will bog down the internet as a result of large resource usage. So let's look at the differentiated services, also known as DiffServ. The DiffServ QoS models specify a simple and scalable mechanism for classifying and managing network traffic. It is not an end-to-end QoS strategy because it cannot enforce end-to-end guarantees. Host forward traffic to a router, which classifies the flow into aggregates, also known as classes, and provides the appropriate QoS policy for the classes. Enforces and applies QoS mechanism on a hop-by-hop basis, uniformly applying global meaning to each traffic class to provide both flexibility and scalability. So in this situation, what happened is, instead of in the previous one, if you remember, the previous one is the integrated services, where we had the QoS node, the end-to-end is aware, and the entire system, from sending to receiving end is basically receiving that QoS, how the QoS should be implemented, and it is explicitly defined across the network, the flow. In this situation, it doesn't do that. So in this situation, what happened is a host forward traffic to a router which classifies the flow into aggregates and classes and provides appropriate QoS policy for that classes. But however, it enforces and applies QoS mechanism hop by hop basis. So unlike the INTSERV, in DiffServ, this is based on hop by hop. This is a very key piece of information that you should remember for your exams and quizzes. If somebody asks you the difference between DiffServ and the other model, you should be able to differentiate that. And how DiffServ is different is that it enforces the QoS mechanism hop by hop basis. So it's hop by hop. So the QoS mechanism will be implemented between the QoS nodes. In this case, the QoS, it would be unaware in this node, and this one would be also QoS unaware. So we call unaware nodes because it is using the differentiated services. You should know the differences between the DiffServ and the other one, the integrated services INTSERV, because it's very important. Remember that in this case, the QoS is aware. The both nodes in the INTSERV is QoS aware. And why do we say that? Because the QoS is explicitly defined, and it is connection oriented approach, and each stream is explicitly defined across the network from end to end, right? Remember that, because it is using the RSVP, right, signaling. But in here, in the DiffServ, differentiated services, unlike the INTSERV, integrated services, it enforces QoS mechanism hop by hop. So The diffserv divides network traffic into classes based on business requirements, and each of the classes can be then assigned a different level of service. As the packet transfers a network, each of the network device identifies the packet class and services the packet according to that class. It is possible to choose many levels of service in diffserv as opposed to the INSA. So some of the benefits of the diffserv is hugely scalable. It's very easily scalable, provides many different levels of quality as a result of scalability as well, because it goes into the scalability. It allows us to have many different levels of services as you expand your network. However, the drawbacks are there are no absolute guarantees of service quality, and requires a set of complex mechanisms to work in concert through the network. So it needs some complex mechanisms for large networks to work together. But however, it is still highly scalable compared to the INSA. QoS Implementation Techniques. There's another video called QoS Implementation Techniques available to you through your Cisco NetAcad. If you do not have access to this video, I will leave a copy of that video on my YouTube channel and a link in the description of this video. As well as I will try to post a card on the top right hand corner, and make sure to watch this video before you move forward with the next few slides. Avoiding packet loss. Packet loss is usually the result of congestion on an interface. Most applications that use TCP experience slowdown because TCP automatically adjusts to the network congestion. Remember, TCP is typically guaranteed delivery compared to UDP, right? Drop TCP segments causes TCP sessions to reduce their window sizes. Some applications do not use TCP and cannot handle drop packets. Basically, those are fragile flows, right? Very fragile flows. So the following approaches can prevent drops in sensitive applications. They include increased link capacity to ease or prevent congestion, guarantee through bandwidth, and increase buffer space to accommodate burst of traffic from fragile flows. WFQ, CBWFQ, and LLQ can guarantee bandwidth and provide prioritized forwarding to drop sensitive applications, as we covered previously. Drop lower priority packets before congestion occurs. So Cisco IOS QoS provides queuing mechanisms such as weighted random early detection, also known as WRED, that start dropping lower priority packets before congestion occurs. So some proprietary QoS mechanisms such as the QoS that comes with the Cisco do have methods where the tail end drops only happens on the low priority packets initially before it start dropping the high priority ones when the system get congested. So you can implement those to try to mitigate those issues with fragile flows. QoS tools. There are three categories of QoS tools as described in the table on your screen right now. So one of the tools is the classification and marking tools. What they do is sessions or flows are analyzed to determine what traffic classes they belong to. When the traffic class is determined, the packets are marked based on that traffic class. So that is the classification and marking tools. Congestion avoidance tools. So what that do is those would use the traffic classes are allocated portions of the network resources as defined by the QoS policy in this situation. And the QoS policy also identifies how some traffic may be selectively dropped, delayed, or remarked to avoid congestion. Like for example, if you have a voice packet and if you have a whole bunch of data packets, it will give still priority to the voice packet over the data packet because the data packet can be delayed. The primary congestion avoidance tools is that wired one, WRED type that I mentioned, the Cisco proprietary one, and is used to regulate TCP data traffic in a bandwidth efficient manner before tail drops caused by queue overflows occur. So it is the congestion avoidance tool is primarily used with that type of system. The tool wired type of system, WRED system, where remember it start dropping the packets from the low priority tail lane first before it's dropping packets from the high priority tail lane queuing, right? Then the next one is the congestion management tools. So when traffic exceeds available network resources, in this situation, traffic is queued to wait for availability of resources. And the common Cisco IOS-based congestion management tools include CBW, FQ, and LLQ algorithms. So in this situation, CBW, FQ, and LLQ what they would do is when the traffic exceed that, what it can handle, the traffic will be queued and wait for the available resources to show up. And as soon as it gets freed up, and it get forwarded through. The figure shows on the bottom of your screen the sequence of QoS tools used when applied to packet flows. Ingress packets are classified and their respective IP header is marked. To avoid congestion, packets are then allocated resources based on the defined policies. Packets are then queued and forwarded out the egress or exiting interface based on their defined QoS shaping and policy. So on the bottom of your screen, you have the ingress interface on the left hand side and you have the egress interface on the right hand side. So the traffic incoming from the left hand side and exiting out of the right hand side. So left hand side incoming and the right hand side exiting. So the first thing going to happen is we are having the classification done here, and then the classification, and once the classification is done, it's going to get marked based on that classification. So that's where the classification and marking happens. Congestion avoiding situation, what's in that category, the policing and selective dropping is going to start to happen right here. Then the congestion management going to do the queuing and the scheduling and shaping. So note the classification and marking can be done on ingress or egress. So notice that the classification and marking can done in either ingress or egress interfaces, whereas the other QoS actions such as queuing and shaping are usually done on the egress or the exiting interface. So classification and marking, these two can done in either ingress or egress. It's going to be okay to do either or, but whereas the queuing and shaping has to be done on the egress or the exiting interface. So keep that in mind. Classification and marking. So let's look at that. So before packet can have a QoS policy applied to it, the packet has to be classified. Classification determines the class of traffic to which the packet or frames belong. Only after traffic is marked can policies be applied to it, because otherwise the traffic flow would not have any way of differentiating. The system won't have any different way of differentiating that traffic flow, right? So how a packet is classified depend on the QoS implementation. The methods of classifying traffic flows at layer 2 and layer 3 includes using interfaces, ACLs, and class maps. So we can use things like the specific interfaces, ACLs, which we have covered in our previous module, and the class map, which I will go into detail later sometime. But those are the options that you have for layer 2 and layer 3. Traffic can also be classified at layer 4 to layer 7 using network-based application recognition. Those are known as NBAR. So layer 2 and layer 3 happens in the interface, ACLs, and class map, while the layer 4 and to layer 7 would happen at the network-based application recognition, also known as NBAR. How traffic is marked usually depends on the technology. The decision of whether to mark traffic at layer 2 or layer 3 or use both is not trivial and should be made after consideration of the following basic points. So remember that. If you are a network engineer or a network technician and you had to make a decision whether to mark layer 2 or layer 3 or to use both, should be determined based on certain considerations that you should look into. Those considerations includes things like the layer 2 marking of frames can be performed for non-IP traffic. Layer 2 marking of frames is the only QoS option available for switches that are not IP aware. So basically, there may be switches that are not IP aware, so the layer 2 would be the only option you would have. Layer 3 marking will carry the QoS information end to end. So if you have a network where end to end you can use the layer 3, then you can implement the layer 3. But end to end, there are some points of your network or hops where only layer 2 can be used. Then maybe you should stick with the layer 2 QoS classifications, because that would make it consistent, right? Works perfectly. So on the bottom of the screen, we have this another table provided to us by Cisco. It shows us the QoS tools, the layer which it operates, and the marking field, and width in bits. So for example, Ethernet, which is 802.1q, 802.1p IEEE standards, use layer 2, and it is the marking field is class of service or COS, and it is 3 bits long. 802.11, it is again IEEE Wi-Fi standard, use layer 2, and it is Wi-Fi traffic identifier, also known as TIDs. Traffic is a traffic identifier, and it has a bit width of 3. MPLS, which is a experimental EXP, which use the EXP marking field, the experimental field in the MPLS, and it has a bit width of 3. IPv4 and IPv6 classification used by IPP, which is IP precedence, it happen in layer 3 and is 6 bits, and IPv4, IPv6 the differentiated service code point marking field, which is also operated on layer 3, but now we use 6 bits. For your exams and quizzes, for if you are taking this class through Cisco, or your instructor is using Cisco NetAcad, for example, you should know which QoS tool will be marking what. For example, if on an exam, if I ask you Ethernet 802.1q and 802.1p standard, IEEE standard, and if I ask you what is the marking field for this, you should be able to pick class of service or COS, as opposed to MPLS is using EXP, experimental, as opposed to 802.11, which is used TID. You should know those things. I haven't seen many questions that actually ask about the width of the bits associated with QoS tool, but since Cisco is actually providing that information here, I would still remember this as well. The only thing you need to remember is the only different bit with this the DSSP. That's all you need to remember. Everything else is 3, right? But I never when I took this class, I have never got a question that asks about the bit the width of the bits, okay? But usually they ask, however, hey, this is the tool, what is the layer which operating in, and what is the marking field. So it could give you like IPv4 and IPv6. One can be asked in the other way, in the reverse way. They could ask like, okay, IP precedence, which one is used in the IP precedence marking field? Ethernet, 802.11, MPLS, etc. And you should be able to pick that up. So that's why this table is very important. Marking at layer 2. So 802.1q is the IEEE standard that supports VLAN tagging at layer 2 on the Ethernet networks. When 802.1q is implemented, 2 fields are inserted into the Ethernet frame following the source MAC address field. So keep that in mind. 802.1q, the IEEE standard, is the one that actually supports the VLAN tagging. So if you have done VLAN tagging in the previous labs at the layer 2 level, the VLAN tagging happening, it is based on the 802.1q standard. So how it is being done is that the 2 fields are inserted into the Ethernet frame following the source MAC address to include that information. So the initial frame gonna have these parts like that, and right after the MAC address field, we're gonna insert the TPID 2 bytes and TCI 2 bytes, the fields, and that will include the 3 bytes used for the COS 802.1p IEEE user priority, as well as the 1 byte for CIF and the 12 bytes for the VLAN ID. So that's how the breakdown happened. Do you need to remember this for your exams and quizzes? Yes, you should, because this is a very key piece of information that you should understand for your exams and quizzes. The 802.1q standard also includes the QoS prioritization scheme known as IEEE 802.1p. The 802.1p standard uses the first 3 bits in the tag controlled information, also known as TCI field, known as the priority or also PRI field. This 3-bit field identifies the class of service, also known as CoS marking. So remember from the previous slide, we have that showing up here as well. TPID, TCI, those two. So in here, the TCI, which is that field, the TCI field on that previous slide, is basically a 3-bit field that identify the class of service marking. The 3-bit means that a layer 2 Ethernet frame can be marked with one of the 8 levels of priority ranging from 0 to 7. So the 0 going to be the best effort, 1 going to be the medium priority data, then the high priority data, call signaling, video conferencing, voice bearer, which is a voice traffic, and then we have 2 reserve traffic. So the lower the QoS value, the lower it's going to be priority, right? Because the higher priority ones are like 5, for example, where it's the voice pairing and video conferencing, which is 4. So for your exams and quizzes, and to understand the concepts that we are covering in this class, yes, you need to memorize this table, including the binary value. At least when I took the diploma degree courses related to this class, I had to memorize this table. This shows up on a lot of exams, including Cisco exams and quizzes. So please go over this slide and make sure that you know this table offhand. For example, if I ask you, what is the QoS value for call signaling? You should be able to tell me it is 3, and you should be also able to provide me with the CoS binary value, which is going to be 0, 1, 1. So you should be able to know that. So you should be able to tell me what is what, and also which one has the higher priority compared to other. So we have 8 levels of priority, well, ranging from 0 to 7, and 5 being the highest level right now, 6 and 7 being reserved, and 0 being the lowest priority, which is basically first in, first out, best effort. And you should be able to know that during an exam. So make sure you memorize this table if you don't understand how this works. Marking at layer 3. So IPv4 and IPv6 specify an 8-bit field in their packet headers to mark packets. Both IPv4 and IPv6 support an 8-bit field for marking. The type of service, also known as TOS or TOS field for IPv4, and the traffic class field for IPv6. So remember that both IPv4 and IPv6 support an 8-bit field for the marking. The type of service, also known as TOS field, is used for IPv4. The traffic class field, however, is a different way of naming it, is used for the IPv6. But it both what it basically both doing is the 8-bit field of marking that packet header. So on the right hand side, we have a image of IPv4 packet header and IPv6 packet header, and in the IPv4 we have the type of service right before the total length of showing up here, and in the IPv6 the traffic class showing up between the version and the flow label right here. So in IPv4 the layer 3 marking is called the type of service, and in IPv6 the layer 3 marking is called the traffic class. So you should know this, and you should know where this is being tagged, which is very important, where this field is in each of those 2 different headers. So remember, IPv4, it's right behind the total length and it's called type of service. IPv6, it's in between the version and the flow control, and it is called traffic class. Type of service and traffic class field. The type of service in IPv4, and the traffic class field, which is in IPv6, carry the packet markings as assigned by the QoS classification tools. RFC 791 specified the 3-bit IP precedence, also known as IPP field, to be used for QoS markings. RFC 2474 supersedes the RFC 791 and redefines the TOS field by renaming and extending the IPP field to 6 bits. Called the Differentiated Services Code Point, also known as DSCP field, these 6 bits offer a maximum of 64 possible classes of service. The remaining 2 IP extended congestion notification, so the ECN bits, can be used by ECN aware routers to make packets instead of dropping them. So the ECN aware routers can be used in this situation as the remaining 2 IP extended congestion notification bits are there to support that. So in here, what you need to know is the concepts behind it. So the RCF 791 has 3 bits, and then the RCF 2474 supersedes the RCF 791 and redefine that. That will allow us to have 6 bits with the maximum of 64 possible classes of service. Those are the key things that you should remember. And on the right hand side, which is basically showing how RCF 791 is different from RCF 2474 standard, where it has 6 bits as opposed to 3 bits here. DSCP values. The 64 DSCP values are organized into 3 categories. They are best effort, which is BE, the expedited forwarding or EF, or assured forwarding. The best effort is the default for all IP packets. The DSCP value is 0 for this, and the per hop behavior is normal routing. When a router experiences congestion, these packets will be dropped. So there is no QoS plan is implemented when the DSCP value is set to 0 and it is at best effort. In expedited forwarding or EF, the RFC 3246 defines the EF as the DSCP decimal value 46, which is binary 101110. The first 3 bits, which is 101, map directly to the layer 2 QoS, where the value 5 used for the voice traffic. At layer 3, Cisco recommends the EF only be used to mask voice packets. So remember that. So best effort is pretty much no QoS, and expedited forwarding EF use the RFC 3246. Assured forwarding, on the other hand, or AF, use the RFC 2597, which define AF to use the 5 most significant DSCP bits to indicate queues and drop preferences. So for your exams and quizzes, you should know the differences between BE, EF, and AF, and how they are differ from each other, and how the BE is pretty much no QoS plan at all. Assured forwarding values are shown in the figure on the right hand side, right here, where the assured forwarding values are displayed here with the low drop, medium drop, with a high drop, with different classes associated with it. And as you can see, the worst queuing would be on the class 1. The best queuing gonna be as you move up this table. The class 4 would have the best queuing. The AXing formula is specified as the first 3 most significant bits are used to designate the class. The class 4 is the best queue and the class 1 is the worst queue. So the class 4 is the best queue as moving up this table, and the class 1 is the worst queue. The 4th and the 5th most significant bits are used to designate the drop preference. So you should know that the 4th and the 5th most significant bits are used to designate the drop preference, while the 6th most significant bit is used to set the 0. So sixth is used for 0. So on the right hand side, you can have that AFXing diagram right here. And we see the class and the drop preference and DSCP field. And for example, we have the DSCP value of AF32, and we have 0, 1, 1, 1, 0, 0, and the DSCP value going to be 28. In this DSCP set of AF32 will have the DSCP value of 28 because of this way that it is set up. So in this example, as I mentioned, the AF32 belongs to class 3, which is binary 0, 1, 1, and has a medium drop preference of binary 10, and the full DSCP value is 28 because you include the 6th 0 bit in binary 0, 1, 1, 1, 0, 0. So that's how the DSCP is configured. I will go over this DSCP values in a separate short video on my YouTube channel and explain how AFXY or AFXing works. So that you will have a better understanding of how this table works and how these values are derived and how they are different from each other. But for now, this is all you need to remember for this module. Class selector bits. The class selector, also known as CS bits, have this type of configuration where the first 3 most significant bits of the DSCP field and indicates the class. So the class selector bits are the first 3 most significant bits in the DSCP field. And it maps directly to the 3 bits of the QoS field and the IPP field to maintain the compatibility with 802.1p and RFC 791 standard. So remember that. The class selector bits are the first 3 most significant bits of the DSCP field and indicates the class. It is result in the indication of the class. And it maps directly to the 3 bits of the QoS field and the IPP field to maintain the compatibility. So on the right hand side, we have the QoS value listed on the most left hand side of this column, this table, and we have the QoS binary value. The class selector is showing right here, which is the class selector bits, and then the CS binary, the class selector binary, and the DSCP decimal values. So depending on who is, depending on the class that you are taking, who is your instructor, you may have to memorize this table, because that might show up on your exam. So what I'm going to do, I will go over the class selector bits as well as the DSCP values, these tables, on a separate short video, because for my exams and quizzes that I have taken for my diploma, this is a very important concept that kept coming back. Not only on quizzes and exams, but also on lab exams, the instructor would ask you these questions. So for evaluation purposes. So what I'm going to do, I will do a separate quick video on the class selector bits as well as the DSCP values later sometime. So stay tuned to that. Maybe you should subscribe to my channel so that you can keep up with these videos. Next, we're going to look at the trust boundaries. Traffic should be classified and marked as close to its source as technically and administratively feasible. This defines what we call the trust boundary. So that is an important concept and you should remember that. So traffic, when you are classifying traffic for QoS purposes, it should be always classified and marked as close to its source and technically and administratively feasible as possible, because that's where we're going to put the trust boundary. So the trusted endpoints have the capabilities and intelligence to mark application traffic to the appropriate layer 2 QoS and or layer 3 DSCP values. The secure endpoints can have traffic mark at the layer 2 switch, because it is a secure endpoint, doesn't have the capability to do that otherwise, and the layer 3. And the traffic can also be marked at the layer 3 at the switches and the routers. So on the on the bottom of your screen, we have this diagram provided by the Cisco. So you have these endpoints. So these are the endpoints, different types of endpoints. So when you have a secure endpoint, the trust boundary will be put it at here, as opposed to in here with where the switches are starting. The trust boundary is right here, and in this case the trust boundary is right before the telephone. So the trust boundary changes based on your configuration of your network. So you could have endpoint access, you can have the endpoint layer or the access layer or the distribution layer as the position where the trust boundary will be located depending on your network infrastructure. So what's really important in this slide, what you should understand is that depending on your network infrastructure, where you're going to mark the trust boundary going to differ based on that. So keep that in mind. So the trusted endpoint have the capabilities and intelligence to mark the application to be appropriate layer 2 QoS and or layer 3 DSCP values. So the endpoints could do that, the trusted one. However, the secure endpoints can have traffic marked at the layer 2 switch. So right here, while the traffic can also be marked at the layer 3 switches and routers, which is something like this. So that's what is showing here. So it can be marked at the trusted endpoint, can be marked at the layer 2 switch, or can be marked at the layer 3 level switch as well. So that's what you need to understand or get out of this slide. Congestion avoidance. Congestion avoidance tools monitor network traffic loads in an effort to anticipate and avoid congestion at common network and inter-network bottlenecks before congestion become a problem. So that's the point of congestion avoidance. They monitor network traffic loads in an effort to anticipate and avoid congestion at a common network and interconnected bottleneck because it needs to be done before the congestion become a problem in that point. So remember that. So they monitor the average depth of the queue. When the queue is below the minimum threshold, there are no drops. As the queue fills up to the maximum threshold, a small percentage of packets are dropped. When the maximum threshold is passed, all packets will be dropped at that point. So that's how the congestion avoidance mechanism works. So some congestion avoidance techniques provide preferential treatment for which packets get dropped. So how the packets will be dropped will get preferential treatment based on certain techniques that you can use in the congestion avoidance. For example, weighted random early detection, also known as WRED, allows for congestion avoidance on network interfaces by providing a buffer management and allowing TCP traffic to decrease or throttle back before buffers are exhausted. Therefore, WRED help avoid tail drops and maximize network use and TCP-based application performance. So keep that in mind. So then the point of congestion avoidance is to sometimes to drop small an amount of percentage of packets before the queue get fully filled up, where you have to drop all packets. So that's the whole point of a congestion avoidance. Traffic shaping and policing. So the traffic shaping and traffic policing are two mechanisms provided by Cisco iOS QoS software to prevent congestion. Traffic shaping retains excess packets in a queue and then schedule the excess for later transmission over increments of time. Traffic shaping results in a smooth packet output rate. Shaping is an outbound concept. Packets going out an interface therefore get queued and can be shaped. In contrast to policing is applied to inbound traffic and on an interface. So keep that in mind. So the traffic shaping and policing are both mechanisms that can be used for QoS to prevent congestion. However, traffic shaping is done on the outbound interface, while the traffic policing is done on the inbound interface. And just like QoS software that provided in Cisco iOS devices, sometimes traffic shaping and policing is also implemented at the firewall level, such as Palo Alto, which a type of firewall manufacturer that has the traffic shaping built into it, and they can also do the same thing as what is described here. So on the bottom of your screen, you have a situation where you have a traffic going up and down, and you have an average traffic rate. By using the traffic shaping, you can actually minimize this up and down traffic into that smooth output. So that's what the whole point of a traffic shaping. So in terms of traffic policing is applied to inbound in the traffic on an interface as opposed to outbound in the shaping, as I mentioned before. So the policing is commonly implemented by service providers to enforce a contracted customer information rate, also known as CIR. However, the service provider may also allow bursting over the CIR if the service provider's network is not currently experiencing congestion. So, for example, if you have the cable internet service provider, and if you are connected to your neighborhood cable loop, where you are connected to their service provider through that, you will have this contracted customer information rate, the customer information rate or CIR, implemented in the traffic policing mechanism in the inbound traffic. So as a result, traffic get limited on the how much traffic in that period of time can be transmitted. However, because depending on the service provider's network congestion during a period of time, the bursting of those traffic may be allowed by using a specified policing techniques. So that's what you need to understand. But really important that you understand is the policing is done on the inbound interface, while the shaping is done in the outbound interface. So that egress interface is the one that is the shaping going to do. Ingress interface is the one the policing going to be applied to. So what are some QoS policy guidelines? QoS policies must consider the full path from source to destination. So if you have two devices communicating with each other, or you are trying to reach a server or something even outside of your network or within your network, the QoS policy, whatever the policy you are applying, you must consider the full path from the user to the destination and destination to the user. So source to the destination is very important. A few guidelines that help ensure the best experience for the end user includes that the enabling the queuing at every device in the path between the source and destination. So there is a consistency between the source and the destination. Classify and mark traffic as close to the source as possible. So that is very efficient in how it will be classified. Shape and police traffic flows as close to the sources as possible. So the traffic shaping and policing should also be done at this close to the source as possible. So these are the best guidelines for applying QoS policies. So that would bring us to the end of this lecture, and I will quickly go over what we have covered today. We learned the voice and live video transmissions create higher expectations for quality delivery among users and create a need for QoS. Without any QoS mechanisms in place, packets are processed in the order in which they are received. When the congestion occurred, the network devices such as the routers and switches can drop some of the packets just to mitigate that issue. Without any QoS, time-sensitive packets such as the real-time video and voice will be dropped with the same frequency as data that is not very time-sensitive, such as the email and web browsing. Queuing packets causes delay because new packets cannot be transmitted until the previous packets have been processed. So we learned two types of delays are fixed, and they include the fixed and variable. Remember, two types of delays, fixed delays and the variable delays. Sources of delay are code delays, packetization delays, queuing delays, serialization delays, propagation delay, and de-jitter delay. Please make sure you know what these are and how they are different from each other. Jitter is the variation in the delay of received packets. And we learned voice and video traffic are two of the main sources for QoS. because voice traffic is smooth and benign, but it is sensitive to drops and delays, and it cannot handle jitter because it will have incoherent communication between the two parties that are communicating over VoIP systems, right? Or multiple parties. We also learned the voice can tolerate a certain amount of latency, jitter, and loss without any noticeable effects. However, the video traffic is more demanding than voice traffic because of the size of the packet it sends across the network. Video traffic is bursty, greedy, drop sensitive, and delay sensitive as well. Data traffic is not as demanding as voice and video traffic. Data packets are often use TCP applications which can retransmit data, and therefore they are not sensitive to drops and delays. Remember, TCP is a reliable transmission mechanism, and therefore the data packet often use the TCP, and hence it can retransmit any data that needed to be retransmitted. The QoS policy implemented by the network administrator become active only when the congestion occurs on the link. So if you can have the QoS policy implemented, but it doesn't mean it's going to get activated until the congestion issues start to happen. Queuing is a congestion management tool that can buffer, prioritize, and if required, reorder packets before being transmitted to the destination. So that is a primary mechanism, primary thing that queuing would do. FIFO, also known as first in first out queuing, buffers and forwards packets in the order of their arrival. So FIFO has no concept of priority or classes of traffic, and consequently make no decisions about packet priority. While WFQ is an automated scheduling method that provides fair bandwidth allocation to all network traffic. WFQ applies priority or weights, what we call, to identify traffic and classify it into conversations or flows. We also learn CBWFQ basically extend the WFQ's functionality to provide support for user-defined traffic classes. So with the CBWFQ, you define traffic classes based on match criteria, including protocols, access control lists, also known as ACLs, and input interfaces. So WFQ allow us to use the protocols, interfaces, and ACLs to define those traffic classes. While LLQ feature brings strict priority queuing, also known as PQ for CBWFQ. But remember, it is recommended by Cisco and many other network engineers to only put LLQ on the voice traffic, because otherwise it's going to get congested as well. There are three models for implementing QoS. They are best effort model, integrated services, also known as INTServe, and differentiated services, also known as DiffServe. INTServe architecture model was developed to meet the needs of real-time applications such as remote video, multimedia conferencing, data or data visualization applications, and virtual reality, while the DiffServe QoS model specify a simple and scalable mechanism for classifying and managing network traffic. The DiffServe design overcomes the limitation of both the best effort and INTServe model. Therefore, the DiffServe may be the best option to use in most cases. There are three categories of QoS tools we covered, which include classification and marking tools, congestion avoidance tools, and congestion management tools. Classification determines the class of the traffic to which the packets or frames belong. And we learn methods of classifying traffic flows at layer 2 and layer 3 includes using interfaces, access control lists, and class maps. Traffic can also be classified at layer 4 to layer 7 level as well, using the network-based application recognition, also known as NBAR, which we haven't covered much in this module. Congestion management includes queuing and scheduling methods where excess traffic is buffered or queued and sometimes dropped while it waits to be sent out at egress interface or exiting interface. We also learned the congestion avoidance tools help to monitor network traffic loads in an effort to anticipate and avoid congestion at common network and inter-network bottlenecks before congestion become a problem. So it is like an early detection system. And we also learned that Cisco IOS QoS includes weighted random early detection, also known as WRED, as a possible congestion avoidance solution. So that is the end of this module. If you like these type of lectures, please thumbs up this video and subscribe to my channel. I will go over some of the concepts that we have covered in a smaller short videos in the near future. Make sure that you go over every single item that we have covered before you take your Cisco exam or quiz. If you have any questions or concerns, please don't hesitate to contact me. And until next time, good luck and have a nice day.